Good morning, everybody. Welcome to a sunny Monday morning of General Chemistry, Chem 1105, with your host, me, Dr. White. Got a lot to do today, a lot to tell you, so I better get started. First of all, you should have seen your scores for test number 2, and I also sent you email with your individual points. I'll be going through test number 2 in a little while today. All right, some changes. I I don't know if I said last week when I do it, but tomorrow I will be doing the gases problem set, and then on Wednesday I will be doing the solutions problem set. And let's see, I got my notes here. Okay, let's go through some important announcements. These are on Blackboard. Let me do this. Thumbs up, people. Do you see Blackboard on Thursday? Thank you. All right, this Thursday, I will be giving test number 3 online. Standard, I'll give it to you right after lab on Thursday. You'll have until 11:30 to finish it and upload it, just like we've done test 1 and 2. Test 3 will cover chapter 5, part 2, and chapter 6, which this is gases and solutions. Now, test has 20 problems, 9 pages. I've brought back, and I have 5 multiple choice questions. Some of the questions are multiple part, like part A, B, and C. Uh, Points breakdown: 48 points gases, 57 solution, and it adds up to 105. So there's 5 bonus points. Tomorrow, I will do a review for test number 3. We'll have our regular meeting on Thursday for the lab, and after the lab, you'll take test number 3. All right, that's one thing I wanted to talk about. Another thing I wanted to talk about, yes, this weekend I was busy grading, plus I had to help my best friend who just moved into a new house. So Dr. White was quite busy. And so I last night, and I put it out this morning, I am offering everybody a lab amnesty. A number of you have not turned in all the labs up to date, and I'm offering a lab amnesty program. If you look in Blackboard and you don't have a score for lab that's already due, then you should email me that lab, or if it's more than one, those labs before this Saturday, 10 a.m., in order for me to grade that lab or those labs, so you'll get points for it. Now, after that date, I will enter a 0 for any lab that was due but not submitted for grading. If you need a copy of the lab, then please email me and I'll send you a copy of the lab or labs for the lab that you need. Now, important thing I do want to mention, and I do apologize, but I have 4, yes, 1, 2, 3, 4 email accounts. One for COD, College of DuPage, one for Elgin Community College, ECC, one for personal, and one I have my own business I consult, and I get on average anywhere from 5 to 40 emails a day. Yes, that many. And because of that, if you have emailed me a past lab and I didn't grade it, email me. And again, I apologize. It slipped through the cracks, but that happens, especially summer is quite, quite busy. All right, now for something really exciting. Hold on. Something really exciting, and that is the extra credit project. And I'm going to switch to student view. Hang in there. If you look at Blackboard, you'll see in the assignment area, it's Chem 1105 extra credit project. And this is an optional project. You don't have to do it. But what is it? I'm opening up a file. Oh, you didn't see it. I'm sorry. Let's do this. There's an extra credit project. Can you see it now? Hopefully you can. And thank you for letting me know. This is an assignment area of Blackboard, Chem 1105 extra credit. There are 2 files. By the way, this is optional project. Now, let's go to the actual project. All right. Thumbs up, people. Can you see on your screen? Chem 1105, summer. Thank you, 2021. Wow, time flies when you're having fun. It's 10 points. Yes, 10 points. It's due by August 2nd. No late projects are accepted, period. How do you get your 10 points? Well, the extra credit project is to create a list of ionic and covalent molecules that are found, this is very important, in the ingredients label list or label of products that you can be purchased, i.e., that means that is things you can use in your daily life, or you can buy in any local store, or even not local store. You must have 5 different molecules that contain ionic bonds, at least one, and 5 different molecules that contain only covalent bonds. You can only use 3 molecules from one product. Now, to get the points, you have to hand in now. Oop, I didn't correct this. I have a printed. Well, yeah, you should hand a printed table, or if you don't have a printer, handwritten, I'll change that, with the product name, the molecule's name in the ingredients list, and if it's ionic or covalent. By the way, be sure to put your name on the table. You'll get 1 point for each correct entry with a total of 10 possible points. Now, to make it interesting, you can't use, remember that, you can't use gasoline. You can't use the molecule water, sodium bicarbonate, carbon dioxide, ethanol, also known as ethyl alcohol. That's the active ingredient in hard liquor and beer and wine, and also gasoline is found in. Can't use sugar. You can't use sodium chloride. You can't use oxygen gas or nitrogen gas. Everything else is fair game. Now, your chart or table should look like this: 3 columns: product, molecule, bond type. And these are examples you can't use because they're using molecules you can't use. But if we looked at a can of Coca-Cola or 7-Up or anything, you'd see water, and that's covalent. If you looked at a can of Campbell's chicken noodle soup, you'd see sodium chloride, and that's ionic. Note, ingredients must appear on an ingredients list on the product. You can't say, oh, the air, well, I already took it out, had oxygen, because there's no, I've never seen a label in the air I'm breathing or on an air tank that tells its constituents, ingredients. And you can't say, well, there's this in a banana, which there are chemicals in a banana you can buy, or strawberries, blueberries, because I've never seen an ingredient list of chemicals in a banana or strawberries or blueberries. This is optional. You do not submit it. Please upload it as a PDF file only or an MS Word file. Now, hint, use Google, or here's a big one, ask your instructor to find out if your molecule is ionic or not. So 10 points. Yes, 10. 10 big ones. It's like adding 10 points to any of your score, your bottom line, however you want to consider it. Now, here's a special, what would I call it? Public service I will do for you. Before you hand in your project, email it to me. I'll check it. And if there's something wrong, I'll let you know that you got to change. And when we're doing a face-to-face, and I've done this face-to-face, I'll tell students either email or bring it in, and I'll look at it, and I'll tell you, no, that's wrong or right. And important thing, listen. If the name of an ingredient has the name of an alkali metal, alkaline earth metal, or other metals like copper, silver, gold, or zinc, lead, it's got ionic bond in it. So if it has sodium, potassium, or lithium, or the other, those are the main, what would it call, alkali metals, it's going to be ionic. Common mistake on the extra credit is, how come I didn't get 10 points? Well, you only put 8 things on your list. Each entry is 1 point correct. To get 10 points, you need 10, yes, 10 entries. If you have any questions, come to my office hours. Remember, my office hours are now 5 to 6, Monday and Wednesday. And if you need extra help, let me know. I'll see if I can squeeze you in sometime when I'm free. Yeah, right in the summer when I'm free. Don't laugh too hard, Dr. White. I won't. All right. Any questions on that? Remember, you have until the due date. That's firm. You won't be able to hand it in after that due date, but you got plenty of time. Normally, I give students 2 weeks to hand it in, which means a week or a little more than a week, actually more than a week, that you'll have to work on it and hand it in if you want 10 points. I recommend you do it because it helps having 10 points in the bank. And that's like adding 10 points to any one of your test scores. Any questions? All right. Let's see. Done that, done that. All right. Something I probably will put out in an email too that I'm not happy to talk about. A couple of the students, and I'm not saying everybody, but a couple, did some minor cheating on test 2. It was minor, so I didn't do what I said in my syllabus, but this is a warning. On test 3, 4, and the final, if I think you're cheating, the fact that I think you're cheating really means I know you, I can, not that I know you are cheating, but more importantly, I could go to the dean of students and the dean of math and science, my dean, with proper evidence to prove a student was cheating. Don't. You get a 0 for that test, or if it's the final, for the final, and it won't be dropped. That's going to really hurt your grade. Plus, I will write a letter, and that will go into your student file, which will not help you in the future when you're trying to get into other schools. So don't cheat. Trust me, I can prove it. Don't. There are only a few of you, but even one is one too many. So you've been warned, do not cheat. You should not talk to other students. You should not look at your notes, and you should not go on the internet. And you shouldn't get help from someone else. And it was quite obvious that one of those happened. And so I feel confident. By the way, unfortunately, in my years of teaching at COD, a couple of times I have to go to the deans and do what I just said. And I had the evidence and they supported me. In fact, one student fought it all the way up to the academic vice president, and my dean brought my evidence. And I also talked to the academic vice president, and there was no doubt when I say someone's cheating, I'm not going to do it unless I have foolproof evidence someone has. So please don't. All right, let's go on to something better. I'm going to go over right now test number 2 answers. Now, some of you didn't do good on test 2. The math, the mole stuff, you just didn't do good. So this tomorrow, Tuesday, I'm going to spend the first half hour of our meeting tomorrow going through a couple of things with mole related to review it to help those who didn't do good do better, and those who did do good, it's a good review. Now, I don't know if I mentioned this. I have never, ever broken a promise to myself. And as far as I can remember, I don't think I've ever broken a promise to anybody else, but I know 100% I've never broken a promise to Dr. White, me. And therefore, I'm going to promise to myself on the final exam, there will be at least 3 balanced chemical equation problems. You guys did pretty good on that, but there'll be a 3-step problem. A lot of you didn't do good on that. And there'll be at least 1 mole conversion, either from moles to molecules, molecules to moles, or moles to grams or grams to moles. And you should know how to do that. And I'll go over that Tuesday, and I may even go over it Thursday. All right, remember, you should never, ever be penalized for an error I make on a test. If you have a grading error, don't bring it up now or question, email me and I'll look at it and I'll get it done by Tuesday afternoon because tonight I'm swamped already and today too. All right, let's get going. Test number 2 was 105 points, but in Blackboard, I only put 100. So you can get a greater than 100% if you see percentage, or you will get 105. I think a couple students, I'm going by memory, got 100 or more on test number 2, and that tells me I did not write an impossible test. A number of people did do good, and some of them didn't. And if you need help, always come to my office hour. All right. About test number 2. All right. Yep, we got time. If I were in your shoes, I'd be asking, well, we've had 2 tests, Dr. White. What grade am I getting in your course? And that's a good question. Now, what I'm going to do assumes you've handed in all the labs up to date or will hand them in. Remember, there's a deadline. And let me open my whiteboard first of all, which I don't have open. Which I didn't open. Hold on. That's weird. There we go. It was hiding behind something else. I'd have to look up, someone asked me what percent. Look in the syllabus, it's there. I don't have it now. All right, everybody see my whiteboard? All right, one method is take your two tests, add them together. Add them together, you'll get a number Z. If this number Z is 90 and above, and this is in my syllabus, you're getting an A. If that number is 80 to 89, you're getting a B. If it's 70, 79 C, 60, 69 D, and less than 659 or less, you're getting an F. Now, since you can drop the lowest test, and a lot of you, this might be, method B, you've taken two tests, look at the higher of those two, let's call it X. And if that's 90 and above, you're right now getting an A. If it's 80, 89 B, 70, 79 C, whichever the higher, 60, 69 D, below 60 or 59 below F. But that's assuming you have added all, you've handed in or will hand in by Saturday, all the labs you've done. And most of you are getting decent scores on labs. Remember, labs are 10 points. All right. Any questions before we take our break?
So our lowest test score gets dropped?
The lowest of the four tests. You're
Okay.
4 tests. So far, you've taken 2, and I should do something. But anyways, let me do something real quick. There we go. Okay. But that will be 1 of the 4s drop. And for most of you, it's usually test 2. I've taught this enough times, I know. With that, I think we should take our break, come back at 5 minutes at 9:56. I went a minute over, bad Dr. White, and we'll continue on with solutions. I'll see you in 5, 9:56. time to get going. It's Dr. White's running late Monday. Sorry about that. All right, let's go through because today I want to finish up solutions. Don't forget, tomorrow we'll do the gases problem set, and on Wednesday we'll do the solutions because I'm going to finish up today. End of the semester like this, it gets a little busy, but we'll still have plenty of time to review for the final. But I got a schedule to keep. You too. All right, let's go back to solutions because remember, because of the lab, I jumped some of it. All right, everybody see like dissolves like? Thumbs up, people. Thank you. All right, remember I taught you like dissolves like solutes are soluble in like solvents, and like which means polar solutes are soluble in polar solvents, nonpolar are soluble in nonpolar. And you should know this is probably one of the most important things I'll teach you. And when we get into organic chemistry at the end of the semester, we'll be using this. And I'll show you how important it is. Now, let me remind you, you should know water is the most polar substances. Salts are polar, like sodium chloride. And alcohol or alcohols, like ethanol, are polar. Non-polar, and this you're going to have to learn. Vegetable oil, Vaseline, gasoline. I'm rhyming. That was an awful joke. Vaseline and baby oil. And finally, dirt and grease. And these are all non-polar. If you mix water and salt, and this is a rule of thumb, not a law, meaning it's about 95 or a little higher percent always true, but it's not 100% true or it would be a law. If you mix water and salt, like sodium chloride, it dissolves. By the way, I should add what you don't know, but I know, which is an alcohol, but not the kind of alcohol you think of, but sugar is polar. Now, if you mix water and vegetable oil, guess what? It's not soluble. Same thing with water and dirt. And later on, I'll tell you how soap plays a role in this. All right, let's look at a problem. All right, can everybody see? 5 points. Compound A is soluble. Thumbs up, people. Let me know. Thank you. Compound A is soluble in vegetable oil, but not soluble in water. What is the polarity of compound A? And the important thing is, how do you know it is this? Your turn. You try and figure it out. Remember, like dissolves like. And when you're done, give me a thumbs up. Or better yet, I can do it electronically. All right, I think everybody's done. So let's take a look at this. What is the polarity of compound A? Well, if it's soluble in vegetable oil, vegetable oil is nonpolar, and you could have done the same for water. And because like dissolves like, because of this, it tells me compound A is nonpolar. And that's how, now if compound B were soluble in water, but not in baby oil, you would know compound B would be polar. So that's how you use like dissolves like. And like I said, we're going to come back to this because like dissolves like is the key. Are you ready for this? How you get your hands clean with soap, how you get your clothes clean with laundry detergent, and how you get anything else you clean with soap or whatever detergent you're using. And that's all because of like dissolves like, and I'll teach you that before the semester's out. In fact, that's probably one of the most important things I'll teach you this semester. All right, let's continue on. All right, switch is totally off for this slide. Everybody see my little picture on the screen? Click, switches off. There's something called electrolytes, which if you ever bought Gatorade and they have their commercials, it's got electrolytes, and those are solutes that separate into ions when dissolved in water. And most of those are, not all, are salts. And a solution of electrolyte conducts electricity, which water that you get from your tap has certain ions in it, which is why people can get electrocuted if they get electricity into a bathtub or into water around their house, and that's not good. So anyways, electrolytes are very important for your body, just keep you alive. And a sad story, I haven't heard in a while, thank goodness, but a number of years ago, every once in a while, I'd hear a story in the newspaper, some TV or radio, so usually it was a radio station, had a contest who could drink the most of either this drink or water, and they'd win $5,000, $10,000. Well, some person would drink an enormous amount of water. When you eliminate it from your body, I think you know what I'm talking about, you also get rid of a lot of the important electrolytes, ions in your body. And when that happens by an enormous amount of water, those people unfortunately died. I think they've stopped that. At least I haven't heard about it in a long time, thank goodness. And non-electrolyte switches off for this too. Solutes that dissolve in water, but don't separate into ions and don't conduct electricity. Example, that would be sugar. All right, solubility describes the amount of solute that can be dissolved in a given amount of solute. Switches on. The solubility of a solute is the maximum amount of solute that will dissolve in a given amount of solvent. You can't put one molecule more in there. It won't dissolve, or it will precipitate out, form a solid at the bottom. And let's look at some solubility, at least one compound. And does everybody see on your screen? Let's see. You should see on your screen sodium chloride from Wikipedia. And if you look at the lower right where I'm scrolling, you'll see properties. And you have sodium chloride. And if you scroll down, solubility in water, 360 grams per 1,000 grams of pure water at 25 degrees C. Water solubility or solubility of anything in the solvent is temperature dependent. And they give you, I don't know why you need ammonia or methanol, but they give that to you. But water being polar, salt being polar, it's quite soluble. And if you tried to put in 360.5 grams, that 0.5 grams won't dissolve because you're at the solubility. That's the maximum amount you can dissolve. And it switches on for these slides. Now, this is very important. There are different types of solutions. You should know these. A saturated solution is a solution that contains the maximum amount of solute that can be dissolved under those conditions like temperature and pressure at which the solution exists. You can't put one more molecule in there because it's saturated, it's full. If you try to, you'll get a solid precipitate. Now, a dilute solution, you should know, is a solution that contains a small amount of solute relative to the amount that could dissolve. If you could put 100 grams in water, a certain amount of water, and you only put 1 gram, that's quite small amount to what you could. And we call that a dilute solution. Next, concentrated solution. That solution that contains a large amount of solute relative to that could dissolve. You're not at saturated solution, but you still have a lot of solute. Remember, solute is one of the components present in a solution that's not in the greatest amount, because the one in the greatest amount is the solvent. And concentrated has found its way for many years into our language. And I don't get any kickbacks, but everybody see on your, let me make sure you're saying it. Yes, you should. Like Minute Maid original frozen concentrate. Until about 15 years ago, maybe a little, give or take a couple of years, grocery stores never sold orange juice or other juices like they do now in a bottle, fully normal juice with the water in it. What they did, Minute Maid was the first, I think, who did it. They concentrated, took out the water, so the pulp and other things that made it taste like orange juice were much higher than if you squeezed it from an orange. And that's why it's called concentrated, because it's a concentrate. It's concentrated orange juice components minus a lot of the water. Do I have time? Oh, yes, I do. Now, I'm not a big orange juice person, but my fraternity house a long time ago, one of my fraternity brothers had an unusual habit. He loved to eat concentrated orange juice. I don't like it. But anyways, he'd sit there with a can, a spoon, and eat it. And it was sort of like you'd eat ice cream or what's another frozen, a snow cone or other things like that. And he loved it, but I still remember that. I still go, not for me. All right, remember, concentrated, you have a large amount of solute relative to what could dissolve, dilute little bit. And by the way, bartenders don't like being told, you know, you just made me a real dilute drink. They watered it down. They don't like that at all. I found that out the hard way years ago when Dr. White used to go to bars. Back when I was your age. All right. Now, we've already talked about this, but an important one is aqueous. An aqueous solution is a solution that switches on up to 1,000 now, which water is the solvent. And it's abbreviated by, let me do it better, AQ in brackets. So if you see AQ in brackets after the name of something, which we're going to go over, that tells you it's an aqueous solution, and you should know the water is solvent. Now, non-aqueous means a solution in which substance other than water is solvent. And you better believe I want my gasoline non-aqueous, because water in there in the winter will freeze your gas line. It'll freeze and you can't use your car. And two, it'll mess up your engine. And gasoline is non-aqueous. So let's go through this again. Saturated solution, a solution that contains the maximum amount of solute that can be dissolved under the condition the solution exists, which means you can't put one more molecule in there because it will precipitate out, form a solid at the bottom. Dilute solution, a solution that contains a small amount of solute relative to the amount that could dissolve. Concentrated solution, you've got a lot of the solute relative to what could be dissolved, but you're not at the maximum level. And you should know aqueous solution, that's the solution designated by bracket AQ close bracket, in which water is the solvent. And non-aqueous, just for your own edification, I won't ask that ever on a test. You said, I don't think I have, but you should still know it. Means the solvent solution is something other than water. And switches off things that affect solubility, what solvent you're using, temperature, what the solute is, other solutes present, and even sometimes the pressure, atmospheric pressure. And again, I'll turn the switch off, but if you've ever tried to dissolve a lot of sugar in water, what do? Heat it up. And the solubility of a substance depends on the temperature. For most, not all, but most, solubility increases as temperature increases. You're adding energy to help hydration. All right, switches on. Now, there's certain things in our daily life you would think, oh, that's a solution. It's a mixture of two substances or more than two that none of them react and it's homogeneous. And the answer is no, it's not a solution. You think it is, but in a solution, they're totally dissolved. Now, hold on one second. I don't have it. Hold on. Sorry about, oops, I just shut my camera off. Sorry about that. I had to get something for what I'm talking about. So you think something's a solution, but it's not. What is it? Well, what is it? It's a colloidal dispersion. And I haven't been subtle all day, so I better start. And a colloidal dispersion, you should know, is the dispersion of small particles of one substance in another substance. It's mixtures in which not dissolve, but it's the different substances are dispersed. Now, this one you don't have to know. Instead of using solute and solvent, we use what's called dispersed phase and dispersing media, not solute and solvent. This you should know. And that's unlike solutions, colloids, which is short for colloidal dispersions, and dispersed light pass through them. And what does that mean? It means light will not go through that. The particles are not totally dissolved and it blocks the light. And what I had to do while I was getting there, remember I told you the first day you'd learn a lot about Dr. White? And one of the things that you're going to learn right now, let me check something. Did you, Colton, did everybody see? Let me go back and do this again. Does everybody see this now? If I didn't have it, I apologize. The colloidal dispersion is, know this, a dispersion of small particles of one substance in another. It's a mixture in which materials are not dissolved, but just in small, tiny, small particles dispersed. And you should know, unlike solutions, colloids or colloidal dispersions disperse light, pass through them. In other words, light won't go through that. Did everybody see that now? And thank you for letting me know. All right, now, told you to learn something about me. And Dr. White is a flashlight freak. I love flashlights. I think I have about 20 or more different types of flashlights. And if I had sugar in here, pop or anything, if you notice, the light goes through. This is a green one. I don't know if everybody can see the green light or it's too bright, but it's going through. Now, if you did the same thing, and by the way, I couldn't find my red one, but here's my white one. You see the lights going through. Now, if this were a bottle of milk and I did this, you wouldn't see any light on my hand. That's because milk is a colloidal dispersion. It's a mixture of fats and proteins suspended in or dispersed in water. But you didn't know that. Now, another one, you should know examples of colloidal dispersions in our daily life. Latex paint is another example. And finally, one, especially good to know around Halloween, but do not test it with a flashlight, is, if you can see any blood veins there. You see that one? Yeah, I think you can see it. Blood is not a solution. It's a colloidal dispersion of amino acids, proteins, and carbohydrates and sugars, mainly glucose, and I forgot what amino acids are going through, that goes to various parts of your body to keep you alive. Now, remember, I'm a chemist, not a medical doctor. Last biology I took was freshman year high school. Not that there's anything wrong with biology, but by then I knew I wanted to be a chemist. and I became one. But you should know one, colloidal dispersion, what it is. Does everybody see this now? I see somebody has their microphone on, so I'm going to help turn it off. But anyways, you should also know that examples of a colloidal dispersion are milk, latex, and blood. And the answer is yes. I can scroll up. Remember, all these slides like this one is available to you in the lecture folder of Blackboard. This one is secretly named Chem 1105, Chapter 5, Part 2. You're welcome. Now, when I talked about it last week for our lab, but I'll go through it now again, a little more detail. If I were to send a couple people into the lab, if we were face-to-face at COD, College of DuPage, and say, make me a salt solution. Well, all of you would do different salt solutions. You have different amount of sodium chloride and different amount of water. Well, how do I make sure if I tell someone I need a solution that is always the same? How do we quantitatively, how much is solvent and solute to describe solutions? Well, there are three types. There's percent concentration, percent by volume, and molarity. The first two, I'm turning the switch off, but I should mention it. Percent concentration is percent mass of a solute, which is, or percent by mass of a solute is percent mass of, or the mass of the solute divided by the mass of the solution, not the solvent, but the solution, which is the mass of all solutes plus the solvent times 100. The greater the percent mass of the solute, the more that's in there. And later on, when we get into organic chemistry, I'll talk about certain bug repellents that if you look at the percent mass or amount of the key ingredient that keeps the mosquitoes away from you, you can find there's a lot of difference in the products. And this is on those labels, closer to the beginning, the more higher the percent mass. Now, another one switches off is percent by volume. And percent volume is volume of the solute divided by volume of the solution times 100. And the volume of the solution is the volume of the solvent plus the solutes. And about the only place I've ever seen this on a frequent basis is on bottles of wine. If you look at bottles of wine, they'll usually have percent volume of the alcohol ethanol in that wine. By the way, Dr. White loves German wines, the white German wines, back from a certain part, Pierce Porter, Golden Trocken, either Cabernet, Spätlese, Auslese. Why? Because I worked in that area of Germany where those wines came from. I found out they're really good. You can get them at Binny's, and they're not that expensive because most people don't know about them. Shh, don't give away my secret. All right, switch is full on. Let's talk about molarity. Thumbs up, people. Can everybody see molarity on your screen? Thank you, Rain. All right, now, molarity, which I talked about last week, but let's go over it. And then some new things I'm going to teach you today is moles of is molarity designated by capital M of a solution as a ratio giving number of moles of solute per liter of solution. By definition, molarity. I don't know where these dots popped up on me. Oh no, I got the dreaded dot virus. Molarity, moles of solute per 1 liter of solution. However, in the lab, we rarely measure by liters. What we measure by is milliliters, and 1 liter is 1,000 milliliters. And therefore, you should know this. Oh, it popped up again. That's for this class. And molarity, you should know. I'll even put 4 explanation points. Know this, molarity, which is designated by capital M, is moles of solute per 1,000 milliliters. Yes, you're going to have to use moles again. And before we do important molarity questions, let's do the following. Let's not do that. We already did it. Thumbs up, people. Everybody see on your screen now, 3 points each. What does this mean? Thank you. And the question is, what does this mean? As soon as you see capital M, that means molarity. What this means is 1.57, and after the capital M is the solute, in this case, hydrochloric acid, and that means molarity 1.57 moles of HCl per 1,000 milliliters. And here's one for you to try. What does this mean? Your turn. Time's up. Put down your pens. I'm just kidding. Capital M, molarity. This says molarity. This is your solute. Therefore, this means 7.02 moles of sodium fluoride per 1,000 milliliters. What does it mean? And what does this mean? And what is the solvent of the solution? If you notice here, bracket, AQ, close bracket, and that tells you the solvent is water. And capital M, molarity, 2.34 moles. And afterward, the solute after the capital M, NaCl per 1,000 milliliters. And I'll give you one to try. And also, what is the solvent? Your turn. All right, time's up. As soon as you see capital M, molarity. And what's molarity? Moles of solute per 1,000 milliliters. So immediately I know, what does this mean? 8.01 times 10 squared moles of potassium bromide, KBr, per 1,000 milliliters. That's definition of molarity. And this AQ in a bracket tells me the solvent is water. And you should know how to do this. Hint. Now, it turns out molarity is way, way useful. And as you learned last Thursday, how to make a molar solution and calculate the molarity, I'm going to be going through some problems now that you should know how to do. Get your attention. Know how to do these problems, really know how to do them. Let's look at the following. There are a number of important molarity questions, like how many moles of solute in X milliliters of a known molar solution? Everybody see my whiteboard? 6 points. Oh no, let me check. All right, now everybody see it? Thank you. All right, now how do you do this? Well, what are you being asked to find? How many moles of sodium hydroxide? NaOH. What are you given? Well, you're given there's 526 milliliters of solution, and you're given this magic number. No, it's not magic number. 1.23 capital M NaOH. And for these types of problems, as soon as you see capital M molarity, what does that mean? I'm going to rewrite it. It's 1.23 moles NaOH per 1,000 milliliters. Because we just did this. What does this mean? And it means this. So now how do I proceed? Well, I only have one real number to start with. I have that many milliliters of solution. And if I had a magic ratio, what would I want my answers units to be? Well, it's moles NaOH. And now, guess what? It's time to use your good buddy, your good friend, unit analysis. Love that whistle. Hope you do too. And therefore, whatever I'm trying to get to goes on top of the ratio. Whatever I'm going to get rid of goes underneath. I'll put those units in. So I have on top moles NaOH. I see somebody with a question. Someone just said, does your dog's ears go up or does he or she run around? Anyways, what we put on the bottom is milliliters. I've got to look at this. Hold on. My sister's a dog person. I traveled too much years ago to have a pet. But I'd go over to my sister's house at times. She had 5 dogs in her house, usually at least 3. All right, now, where do we get these numbers? We look right here, and we have 1.23 moles of sodium hydroxide per 1,000 milliliters. Now, this is 1,000, an exact number, because it's part of the definition. This is not. So this is 3 significant figures. 3 significant figures. My answer should be 3 significant figures. Before I go any further, milliliters divided by milliliters cancels out, because anything divided by itself equals number 1. And I'm left with moles of NaOH. And now, if I can find my calculator, and I just did, turn it on, clear it. And my calculator gives me the following number. And I'm going to let you round this off to 3 significant figures. Time's up. Keep the 6, keep the 4, keep the 6. That's my 3. Use the 9 to round off. That's 5 or higher. Drop that, that increases. So the correct answer would be, hold on a second. I don't like the way that 4 looked. 4.7 times 10 to the minus 1 moles of NaOH. And the beauty of having certain molar solutions around, if I needed these many moles of sodium hydroxide and I had this stock solution, I just measure out 526 milliliters, and it makes your life a lot easier. And if you go into the stock room as COD or other colleges or other research labs, you'll find stock solutions of different molar solutions of different chemicals. And that's how we use it. I keep on wanting to write, and I promised one of your colleagues I'd print. All right, what I ask you to do first is write down in the area right here, or wherever you want, what are you being asked to find? What are you given? All right, time's up. Let's do it. You're being asked to find how many milliliters of an HCl solution. What are you, hold on. What are you given? You're given how many moles you're trying to get. And you're given this, the molarity. As soon as I see this, because it's a capital M molarity, I know that's 1.33 times 10 squared moles HCl per 1,000 milliliters. And therefore, the only number I have really to start with is this. So I will. And if I had a magic ratio, not magic, it's unit analysis, what units do I want my answer to be? We have this right here, milliliters of HCl. And now I'll use my good buddy, my good friend. Let's see if I can get somebody's dog to pick up their ears. Unit analysis. And whatever I'm trying to get to goes on top of the ratio, and whatever I'm trying to get rid of goes underneath. And I'll write that in. Here I have milliliters, and down here I have what? Moles of HCl. And where do I get those numbers? From this. For every 1,000 milliliters, there's 1.33 10 squared moles of HCl. And moles divided by moles cancel out. I'm left with milliliters of HCl. That's my solution. And remember, A divided by A equals 1. And I can pick up my calculator now, clear it. And remember, I see a question or comment. Let me do that. Hold on. Then I want, you're right. Someone caught me making a mistake. Thank you. This should be 10 to the third. This should be 10 to the third. Let me start again. All right. Well, my, for some reason, I'm getting a syntax error. I usually don't, so what I'm going to do is go to my spreadsheet, which doesn't give me a, and what I get, and sorry for going a minute or two past the deadline of our break, but hang in there. And what I get, my calculator, actually my spreadsheet is 10 to 0 is 1, but you can keep it, round this off to 3 significant, 3, 3 exact number. Keep the 3, keep the 8, keep the 4, use that to round off, it's 4 or less. And it'd be 3.84 milliliters. And with that, let's take a break, come back in 5 minutes at 3:57. I'll see you in 5, 3:57, 3:57, what am I saying? 10:57. That'd be one heck of a break. Time to start. I'm back. Now, molarity, like I said, is one of the most important concepts in chemistry in the sense that it makes our life easier. All you have to do if you have stock solutions of different molarity, remember capital M, you just measure out, you don't have to weigh it, you go by volume. And it's very useful to do. Now, when you make it, I showed it to you on Thursday, but I didn't show you this one for my personal collection. This is a 25 milliliter volumetric flask. You put your solute in there. Then if it's in water or whatever solvent, you fill it up. I don't know if you can see the line right there. And this is very accurate. This one, they don't have the accuracy, but usually it's for 25 milliliters, probably 0.1 accuracy, plus or minus 0.25, or probably even better than that. But anyways, isn't that cute? Now you know I'm a chemist. It's part of my collection in my living room of different glassware and things like that that I bought from eBay. No, I didn't steal it. And eBay is a great place to get used equipment, or I worked in labs where we're throwing out stuff. Can I take it? And they say, sure, and I do. All right, let's get back to molarity. Now, normally you make solutions either multiples of 5, but to help you with significant figures, I'm going to do something a little different. 10 points, yep, 10 points. How many grams HCl are needed to make? And let me do this one, then I'll let you try one to set up. The question is, how many grams HCl are needed to make 433 milliliters of a 8.99 capital M HCl solution? Does everybody see that on your screen now? Thumbs up, people? Oh, no. Yes, thank you. Boy, this is a delayed action thumbs up people group. All right, so what are we being asked to find? How many grams of HCl? That's what it says right here. What are you given? Well, you're trying to make 433 milliliters of the solution, and you're given this 8.99 capital M HCl. Now, before I go any further, capital M, molarity. I know this means 8.99 moles HCl per 1,000 milliliters. Now, if I were to set up, can I go in one step from milliliters of solution to grams? And the answer is no. You need 2 steps. You can't do it in one. And now let me open up something, then I'll Does everybody see important information on your screen? Thank you, Ashley. All right, this is for test 3. I recommend if you go to the lecture folder of Blackboard, look at the file, important information, test number 3. And you'll see I give you 1 mole of an element equals atomic weight, 1 mole of a compound, molecular weight is the sum. Ooh, molarity, moles of solute per 1,000 milliliters. Then I have the molarity 2-step problems. I also have stuff for the gas laws we'll talk about tomorrow when I go through the gas laws problem or gases problem. And the first step is milliliters to moles, and the second step is moles to grams. So when you have to do 2 steps for molarity, milliliters to moles and moles to grams. So the first step, I go milliliters to moles. And the only milliliters I have is this. And why don't you fill in the rest right here? What units you're trying to get to, what units go here, and what numbers. And I'll let you try that first. All the information you need for here is located right here. We're just doing the step 1 only right now. Give you another 25 seconds. Go. Three, two, one. Blast off. No. All right, let's do this. What are we trying to get to? We want to get to moles. So we need moles of HCl. Use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. And I'm going to write those values in, or the words, moles, HCl, milliliters. Where do I get these numbers? From the fact that you know 8.99 capital M HCl really meant 8.99 moles of HCl per 1,000 milliliters. And milliliters divided by milliliters cancel out because anything divided by itself equals number 1. We're left with moles of HCl, which we want to get to. And I'm going to use my spreadsheet because it's nicer to me than my calculator. And when I do the math, my calculator gives me a number, 3.8926700 times 10 to the 0 power. I'm going to round it off. Remember, this is 3 significant figures, 3, and the 1,000 is an exact number. There should be 3 significant figures. Let me look at my spreadsheet again. And that would be 3.89. Now, when we have more than one step, there's two philosophies: round off at each step or round off at the end. For those type of situations, I will, guess what? Do it both ways, because I'm not going to force you to do it like I am, a round off at each step person. Now, if we go back here, the second step of the molarity two-step problems is moles to grams. So let's go back here. Step 2. And what do we have? We now have 3.89 moles of HCl. What are we trying to get to? You put here and just put the units in for that ratio. Use your good buddy, your good friend, unit analysis. This is something you should have learned for test number 2. Not asking you to put in numbers, just what units are you trying to get your answer in, and what are you trying, what goes in that ratio. And let me help you out. Remember, what are we trying to ultimately get to? Grams of HCl. I'm watching the seconds tick off. Actually, they don't tick on a computer, but you know what I mean. All right, let's do this. Question is, how do you set up step number 2? Step number 2 is you're going moles of HCl, which we just calculated. We want to get the grams of HCl, our answer. And now we'll use unit analysis. What we're trying to get to goes on top. What we're trying to get rid of goes underneath. I'll write that in. Grams of HCl, moles of hydrochloric acid, HCl. 1 mole, where do I get those numbers? You go and look at important information, test number 3. And 1 mole of a compound equals its molecular weight in grams. The molecular weight of that compound is the sum of all atomic weights. See, I'm cut down in memorization, but you still have to know how to do this. And let's go back here. What's the molecular weight? Whoop, wrong color. What's the molecular weight of hydrochloric acid? 1 hydrogen, 1 chlorine. This is 1.01 atomic weight. The 3 significant figures, 35.5. Add it up, 36.51. 2 past the decimal, 1. Keep the 5, use the 1 to round off. So for every 1 mole of HCl, there's 36.5 grams. Notice this is 3 significant figures. Oh, I'm in my rut. This is 3 significant figures. And this is an exact number because 1 mole equals is a definition. And now I can go to my calculator, which I will. But first I have to sneeze, excuse me. And let me show you my calculator. So everybody see the yellow on your screen? And now I'm going to get fancy. I can do this because I've been using a spreadsheet for a long time. And everybody's seeing red, the two numbers from column A and B. Thumbs up, people, help out. Thank you, Ashley. And if I round this one off, it'd be 1.42 times 10 squared. And if I round the other one off, it would be 1.42 times 10 squared. So whether you round off at the end or at each step, you get the same thing. So the answer here, the final answer, which is what you're trying to get, and this is a standard calculations chemists make all the time. When you want to make up a certain amount of a certain molar solution, you do the two-step. Let's go through it. The problem was how many grams of HCl, hydrochloric acid, are needed to make 433 milliliters of an 8.99 capital M HCl solution. You need two steps. And the first step, you go from milliliters to moles of whatever you're trying to find. Step two, we want to get grams because that's what we weigh out in a lab. So you want to go from moles to grams. And it's always this way for this type of problem. Let's do another one. Hold on 1 second. Somebody's got a question. Uh-oh. Thank you. All right, now can you see it, everybody? Thumbs up, people. Help me out. Can you see 10 points on your screen right now? Thank you. I'm going to have to give you guys a prescription to go out and eat some thumbs up faster food. That was awful joke. I apologize. All right, let's do it. How many grams of NaOH are needed to make 125 milliliters of a 4.42 times 10 squared molar, oh, I gave it away, capital M, NaOH solution? All right, first of all, right here, write down what are you being asked to find and what are you given. You got 30 seconds, go. Nice of me, aren't I? Give you a bonus 10. Time's up. What are you being asked to find? Right here, how many grams of sodium hydroxide? What are you given? You're trying to make 125 milliliters of solution, and you're given this number, capital M. I'm having a bad writing day. Sorry. NaOH. And it's immediately capital M, molarity. What does that mean? 4.42 times 10 squared moles NaOH per 1,000 milliliters. And as soon as I see milliliters and grams, I'm trying to get to grams, and I'm given milliliters, I know you need 2 steps. And those 2 steps are found in important information, molarity 2-step problem. Step 1, milliliters to moles. Step 2, moles to grams. And the only thing we have to start with is 125 milliliters. I'm going to let you fill in the rest, like what units you're trying to get to and what goes here and here. Your turn for step 1. Go. All right, time's up. What units are we trying to get to? Moles. But moles of what? Sodium hydroxide. I use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. Whoops. Moles of sodium hydroxide and milliliters. Where do I get these numbers? Because I took the time to see capital M means molarity. And what does that mean? It means this. 4.42 times 10 squared moles of sodium hydroxide per 1,000 milliliters. Notice milliliters cancel out. I'm left with my right units. So now I'm going to go to my spreadsheet. First of all, I'm going to clear it out. Next, I'll put in my numbers and show you after I've done that. And you should see on your screen right now my spreadsheet. Thumbs up, people. And notice I have three exact number. So I'm going to round this off to 3 significant figures. That'd be 5.52 times 10 to the first. Don't worry about the extra zeros. That's just the way I have it. And now that would be how many moles of sodium hydroxide I have, which would be 5.52 times 10 to the first moles NaOH. And yes, I did round it off correctly. All right, thumbs up, people. You see my whiteboard again. Now we have to do step number 2, moles, 2 grams. And I have now 5.52 times 10 to the 1 moles NaOH. And you learned this, I hope, for test number 2, sodium 23.0, oxygen 16.0, hydrogen. Yes, I do know these by heart, because I've done this so many times. I know this number, and I'll help you out. That would be 40.01, which the molecular weight of sodium hydroxide is that, 40.0. And you figure out what units you're trying to get to and what goes on top and bottom of this ratio. Your turn. And let me just remind you, what are we trying to find? There you go. And instant replay. There you go, grams of sodium hydroxide. You don't have to calculate it, just put in the number. All right, time's up. Let's go. What are we trying to get to? Grams what? Sodium hydroxide. I'm gonna use my good buddy one more time. Excuse me. My good buddy, my good friend, unit analysis. Do an extra one for good measure. And how do I do that? Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. That's grams NaOH, moles NaOH. Where do I get that? 1 gram equals the molecular weight, 40.0. This is an exact number. This is 3 significant figures. Oh, I'm in my rut again. And this is 3 significant figures. So my answer should be 3 significant figures. And now I know what to do. I go to my spreadsheet. And now, since there are 2 ways of rounding off, I have 2 columns. And it turns out I get the same answer if I round off at the end or each step. That's 2.21 times 10 to the third. And therefore, my answer is both ways 2.21 times 10 to the third, or that would be 2,210 grams. But this is, by the way, let me rewrite this because let's see if I can do this. That's better. And that's how many grams of sodium hydroxide. And you go out, weigh this out, put it in a volumetric, add enough of the 125 milliliters, and that's the solution you'd get. And that's how you use molarity. And you should know how to do that. And that's really question 4 here, which is the most important. How many grams of solute A are needed to make X milliliters of a known molar solution of A? And that's what we just did. Hint, you should know how to do that. The other two I put down there, but 1 and 2 we did, 3 is rare. So anyways, oh no, guess what? We're at the end of this chapter. And you know what that means, don't you? It's new chapter time. And this chapter won't be on test 3, but it will be on test 4 that's coming up. And first I got to open it up. As everybody see chapter 7, acids and bases, on your screen. Thank you, Ashley. All right. This chapter is probably one of the most useful things I'll teach you this semester for the rest of your life. Acids and bases. Oh, that's chapter. What's an acid? What's a base? Well, it turns out that's a very hard question to answer. And about 100 years ago, switches off for this slide. Switches off. A chemist named Arrhenius came up with an acid-base theory. And the theory was an Arrhenius acid is a hydrogen-containing compound that in water produces the hydrogen ions H+. And an Arrhenius base is a hydroxy-containing compound, hydroxy meaning OH, or hydroxide-containing compound, OH minus, that in water produces the hydroxide anions, or ions. It's an anion, but I just put down. And I'm not going to do any examples because nobody uses this theory. Now, turning the switch on. Now, I'll never ask you the name, but I'm going to show you the structure, and you should know these are acids. Hydrochloric acid is HCl. Sulfuric acid, which is probably the most heavily used acid in manufacturing in the United States, not the world, is H2SO4. That's an S. Nitric acid, which is also important. And acetic acid, which I got to think about. Hold on. This is the actual structure. I don't know the empirical formula because I never use it. And this is acetic acid. Why is this important? 4% of this. Because you have acetic acid in your house, plus 96% water, you have vinegar. Vinegar is a dilute solution of acetic acid. But you should definitely know these right here, that HCl is an acid, H2SO4 is an acid, HNO3. And these are key acids in our daily life. And lo and behold, your stomach has cells that make hydrochloric acid, and that helps break down your food when you eat it. You should know this for test 4. Remember, tomorrow we'll have our lab. Don't forget about the lab amnesty program. Don't forget that tomorrow, the first 15 minutes, and I'll do it again Thursday, I'm going to cover in depth again the mole stuff on test 2 that a lot of you had problems. So show up or watch the video. Now, there's certain key bases you should know. And I don't mean the names, just the structures that this is a base. And the first one, which had the old name, a lie, but it's sodium hydroxide, is NaOH. Next one is potash, which is really known as potassium hydroxide. Ammonia is a very strong base. And one that I like you to know that's really baking powder is sodium bicarbonate. I'll never ask you the names, but you should know these 4 are bases. So we have acids and bases. Here are the key bases. I just gave you the key acids. Anybody need more time to copy this down? Send me a message via chat like, whoa, don't move yet. All right. Now, there's a big problem with the Arrhenius theory, and it does not explain acids or bases in non-aqueous solutions. What happens when the solvent is in water? Well, you can't use the Arrhenius theory, and therefore switches on, next slide, big time. Bronsted and Lowery, 2 chemists independently, and it's named after both of them, came up with the same theory called the Bronsted-Lowery theory of acid-base theory. And this is stuff you should know. What is a Bronsted-Lowery acid? It's any substance that can donate a proton, we call proton H plus, to something else. And you should know a Bronsted-Lowery acid is a proton donor. A Bronsted-Lowery acid is a proton donor. It gives up a proton. If I'm a Bronsted-Lowery acid, I'll say, here, take my proton. I'm an acid. I'm a Bronsted-Lowery acid because I donate H plus. Take it. I'm an acid. Now, what's a base? Just the opposite. A Bronsted-Lowery acid is a proton, any substance that it can accept a proton from other substances. And you should know that if I'm a proton acceptor, I'm a Bronsted Lowery base or just a base. Acid proton donor, base proton acceptor. What is a proton? H plus. And you should know this. Don't rush, because guess what? You make a mistake. An acid is a proton donor, a base is a proton acceptor, and a proton is H plus. And with that, I'm out of time. Remember, tomorrow, the first 15 minutes or so, I'll go through a problem, key problem on going from grams to moles or moles to grams. On Thursday, I'll do another one of the 3-step problem because I promised myself, which means those are going to be on the final. Tomorrow, we'll do the lab with acids and bases of foods. Ooh, we're going to get into some dangerous chemicals like ketchup, mustard, and vinegar. Ooh, dangerous stuff. Anyways, with that, I'm going to say gang gesund. Goodbye. Don't forget, I have my office hour tonight from 5 to 6. If you need any help, come on by with anything dealing with this course. I'll be there. With that, I'll see you tomorrow. Gang gesund. Goodbye.